Welcome back to The Explainer. I want you to take a quick look around you right now. Literally, everything we do in our modern, perfectly balanced world relies completely on the electrical grid. It's this massive, incredibly complex machine sprawling across continents, just silently powering our homes, our hospitals, our entire lives. But what happens when that fragile, perfect balance is violently broken? Well, today we're going to explore the exact anatomy of an electrical disaster, relying on real engineering analysis to understand what actually happens when power systems go dangerously wrong. So, if we map out the normal journey of electricity, it's pretty straightforward. We start with the generators on the left, push through step-up transformers, travel down transmission lines, hit the step-down transformers, and finally reach the loads, which is us using the power. Under normal, safe operating conditions, this massive network is incredibly calm. Voltages and currents stay exactly within their standard ratings. It's a completely harmonious, controlled flow of energy that we just totally take for granted every single day. But man, when that perfect balance is violently broken, we are not just talking about some abstract math problem on a whiteboard anymore. We're talking roaring fires and total chaotic destruction. Just look at the devastating contrast here. You've got an explosive substation fire completely engulfing a transformer right next to an arcing, violently sparking electrical pole. This is literally what happens when massive amounts of energy suddenly escape their intended controlled pathways. But don't worry, we're going to break down exactly how and why this chaos happens, step by step. For today's agenda in this explainer, we'll cover the calm before the faults, causes of grid chaos, the shocking real-world effects, open versus short circuits, and finally, the most common faults. Let's just jump right in.
Section 1. The calm before the fault. Normal operations.
Right, so what exactly is a fault? In engineering terms, a fault is that terrifying split second when manageable energy just stops following the rules. It's any abnormal condition where equipment, like a transformer or generator, electrically fails. The second that happens, your voltage and current instantly deviate from their safe nominal ranges. Basically, the energy goes completely rogue. Which brings us to Section 2, causes of grid chaos. What actually triggers these disruptions? You'd probably think it takes some massive, world-ending event to bring down a system as robust and heavily engineered as our power grid, right? But the reality? The reality is often surprisingly ordinary. We're talking lightning strikes and severe weather, sure, but also birds, birds and small animals climbing into sensitive switchgear where they definitely shouldn't be. Then there's cars physically crashing into poles, or simple human error like a technician literally just leaving a metal wrench behind after a maintenance check. And of course, there's just plain old aging insulation and equipment breakdown. Both nature and our own everyday mistakes are constantly threatening the grid. Moving to Section 3, the shocking real-world effects, the devastating impact. So what physically happens to the real world when all that current escapes? Well, it is truly terrifying. You get this massive overcurrent flow because the electricity finds a new, ridiculously easy path, drawing a huge amount of power. This instantly creates a deadly shock danger for anyone nearby. We're talking total loss and literal burning of equipment, severe disturbances ripping through the interconnected circuits, and, as we saw earlier, devastating electrical fires. The sparks actually ionize the surrounding air, which leads to those massive violent explosions you see in transformers. Section 4. Open versus short circuits. The two battlefronts. Okay, so looking at this, it perfectly illustrates our first battlefront, the open circuit or series fault. This simply means a conductor has physically broken or snapped. You can have a single-phase open circuit where just one line breaks, or two-phase, or all three. Now, these absolutely cause abnormal operation and heavily stress the system by pushing voltages up. But honestly, these usually aren't the massive, explosive events that make the evening news. On the flip side, we have the short circuit, also called a shunt fault. This is an abnormal connection with very low impedance between 2 points. Basically, think of it as electricity finding a devastatingly easy shortcut. These are by far the most common and most severe disasters engineers face. Because the resistance is so incredibly low, massive currents flow through the lines. If a short circuit is allowed to persist for even a tiny fraction of a second, the resulting heat will completely melt and destroy the equipment. And finally, Section 5, the most common faults, categorizing severity. Here is where it gets really interesting, because engineers categorize these short circuits into two specific types based on symmetry. First, symmetrical faults. These are thankfully super rare, only about 2 to 5% of all faults, but they are absolute grid destroyers. The system technically stays balanced, but the sheer volume of current across all three phases will just obliterate the equipment. Then you have unsymmetrical faults. These are incredibly common, generally far less severe, and they unbalance the system because each phase ends up with a different impedance. They are basically the everyday nuisance that grid engineers are constantly managing. So breaking down those common unsymmetrical faults, it's really all about what wires are touching each other or touching the Earth itself. We've got line-to-line faults, where two phase conductors short together. Double line to ground, where two lines short and also touch the Earth. And lastly, the single line to ground, or LG fault, where just one single wire makes an abnormal connection with the dirt. Which brings us to a pretty staggering number, 65 to 70%. Astonishingly, almost 70% of all faults on the entire global power grid are just one single line touching the ground, that LG fault. Whether a tree branch falls on a wire or a ceramic insulator cracks and lets the current arc to the metal tower, this single, unbalanced connection to the Earth makes up the vast majority of every grid disruption we ever experience. You know, it's honestly a miracle of modern engineering that we can automatically detect, isolate, and survive thousands of these ground faults every single day without the whole electrical system collapsing. We are absolute experts at surviving that 70%. But when you really think about the sheer destructive power of a perfectly balanced three-phase short circuit, it leaves you wondering. As our energy demands skyrocket and our infrastructure gets older, is our illuminated world truly ready when that rare, catastrophic 2% finally hits? I hope this gave you a whole new respect for those power lines outside your window. Thanks for joining me on this explainer, and I'll see you next time.